and I'm gonna like start right away. So you may wonder why I decided to go with like a painting from Gauguin, knowing like I will not talk about art. It's just because of like the name of this famous painting. It's called like Where Are We From and Where Are We Going? And I thought it would be like the perfect illustration of like many aspects I try to like address with my research by looking at trace element in very old rocks, if I were to summarize. And some of my research address the first question, which is like where are we from, coming from, and the other about the critical elements we'll see like address where we're gonna go. So I want also to start by saying this is a teamwork, and I'm very like lucky to like work with like a huge group in US, but also like in many other countries, and I cannot like I will have to list like almost like 3 slides of collaborators. So like, but I will make sure to thanks like the lead author as often as I can. So what are like critical metals? We are all facing this dilemma as modern society to move away from our dependence to like the oil and gas, and for that we need to like switch to the green energy. But because all the nation wants to do it at the same time, it creates a huge demand on like a lot of critical metals that are going to be required for what we call the green energy transition. This is just like a list, and just as a context, I'm going to show you also like a periodic table highlighting like the many like elements that are required and acknowledged as critical metals by US or like in Europe, Australia, Japan. As you can see, like as I used to say, 3/4 of the periodic table basically is going to be like critical metals. When we try to secure critical metals as a nation, we are not dealing with like the same resources. China is very lucky and has access to a lot of those. In US and North America, it's not that bad, but some other like continent and or like smaller nation, they are going to have to like find new solutions, and among that, it's because like again, depending on where you is, for example, here like this is a list for US, you are not gonna like come with the same list. But again, here I want you to realize that to support the green energy transition, we're gonna need like a lot of these resources. So how do we do the mining currently? This is an example of an open mine where I was not too long ago, and right now 100% of the effort is economically driven, and the mining company, they are just going to look for like what they call ore deposit. I will come to later to what is that notion. And when they're going to look at let's say a deposit of cobalt or anything, they're only going to consider the grade, or in other words, like the concentration. But as you can see, there is a strong economical aspect that of course like control where like the mining company is going to like mine, but to promote sustainable mining and even a sustainable earth, maybe we need to move away from that, because right now like the way we currently like mine these resources, it's an environmental catastrophe, and the way like the exploration is done is very basic. You know, the way like they mostly consider like this ore deposit and neglect like what we're going to talk as alternative deposits or even recycling. It's often like also very black and white, you know, between like the information they consider, and they tend to assume like a metal or like it's going to behave like in a homogeneous way in the matrix, and this is not the way it works, unfortunately. So today I'm going to focus on one of the like unconventional reservoir for critical metals, mostly the black shale. But just so you know, also like we have ongoing works at the Star Lab with like soil, we would call that metal farming, and also groundwater. So this was the first kind of short context basic introduction about the future, you know, like, and the future is we're going to need these critical metals. Now let's look at our past, and by that I mean like the origin of life, because the origin of life is so tied to like the rise of oxygen on Earth. So how do we study that? We rely on Paleo-Redox proxies, and these elements ideally are going to be like buried in environmental archives. And in a perfect world, or in a perfect scientific studies, these geochemical tools should be, of course, redox sensitive, directly recorded in the environmental settings, relatively easy to analyze, and of course, this is where it could become tricky. The whole entire community should agree on how we interpret the signal. As I showed you also for like the critical metals, you can look at the periodic tables, or as I like to call it, the greatest toolbox on Earth. And for like the Paleo-Redox proxy, everything started with like just using the main element, carbon and sulfur concentration, and also isotope. And something changed like 25 years ago, when like it became possible to like analyze the non-traditional isotope. So we had huge hope for iron, but it turned out to be extremely difficult to interpret the data. But many other like Paleo-Redox proxies showed up and are very promising. So why do we need them? Because, for example, at the panel at the top, this is like a representation of what we think happened on Earth regarding the oxygen concentration in the ancient atmosphere. And basically, you can see like we had like 3 stages. Here, 1, which is going to be like before like the Archean, 2, Proterozoic, and Phanerozoic, which is like only, when you think about it, quite recent. And below, I showed you some example on how like some studies have used one of these proxy chromium isotope or rhenium concentration to try to like assess what was like the redox condition, EI, the oxygen level in the ancient Earth. So how do we currently use these proxies? I know like some of you today are like champion in using this proxy to reconstruct like the Earth's history. And we start with the concentration. We're going to look at our whole rocks, sediment. It could be also like trees, you know, like it can be any environmental archives. And just by like addressing the question, hey, is it more enriched or depleted? It can inform a lot. And just this approach led to great publication. Then, as I said, with like the availability of like the non-traditional isotope, we were able to add another dimension. And the isotope also like when properly used, allowing to like make some model about either the type of processes involved or also like the source and the sink. But right now, the way like we're going to call that the paleo community like uses this proxy is just like to say oxic, or like anoxic and oxenic, and they're going to sometimes use ferruginous. In other words, they mostly concentrate on like the top, and you see like the purple and the red zone. I want today to make like a statement. They should move away from this definition and try to like embrace more like a chemical way and just address and refer to like this ancient redox condition by what was the redox couple that was controlling the redox chemistry, in other words, like the electron acceptor. So again, here, I want to like, in my opinion, highlight the limitation on how like we use, even I like when I cannot do otherwise, like the Paleo-Redox proxy. There's still a lot of speculation. Again, similar like remark like I did for like the critical metal, lack of nuance, quantitative information. And here even worse, because we are trying to interpret the past, misinterpretation and oversimplification. So what I wanted to convince you is like either if you study the past or like you are here to secure like a very highly demanded resources. Right now, I think like all the scientists like studying trace element geochemistry, they tend to ignore like the mechanistic processes. It's going to be like responsible for like the sequestration and or like the remobilization. And because of that, any potential interpretation of enrichment or like isotopic fractionation are going to be biased. And so like it could impair like our effort to like either like look at the past or like secure like critical metals in a sustainable way. So I propose to add a third dimension. And of course, I'm not the only one to do that, but like somehow like it takes like a lot of repetition to make sure like the word got out. And so again, in addition of the concentration and isotope, one thing that the synchrotron can be like fantastic in adding to like this type of research is speciation. And of course, like the mapping. But for like today's talk, I decided to like mostly focus about this molecular aspect. So I'm going to start like the first part. Now let's dig into the data with like vanadium, but not vanadium as a Paleo-Redox proxy, vanadium as like a critical metal. It's going to be like, it is already in high demand because in alloys, in like the aerospace industry, and also like in some type of what we call large batteries and many other applications. So we need to like secure these critical metals. So what do we know now about like the vanadium speciation? And here, if you like want to try to figure out the mechanistic processes, often we're going to rely on thermodynamics. And this is great. I teach that special dedicates to like my students who are probably like watching that now. We're going to spend a lot of time like learning and exploring thermodynamics. It's great, but one of the weaknesses of that approach, you rely on constant availability. So if you take any of the latest review right now, this is what people are going to tell you about vanadium speciation, either in water or like solid phase sediment. You have 3 redox spaces, like 5, 4, and 3. And you can see it's going to form like this oxide or oxyhydroxide. That's it. But no one has tried to measure like vanadium speciation. So is that true? So in collaboration with like Dr. now like Liebo Bian, now like a postdoc in China, we looked at one of the greatest shale, like to like answer this type of studies, the Alum shale in Europe. I'm just showing you the location. And we were lucky to have access to like different wells. And for like the story I'm going to tell you now, we're going to focus on this one here, like the green one. And why is that? Because also like back in the time, it was what we used to call like the Baltica. And we decided to focus on this one because when we look at the concentration, here we are like what we call between the Cambrian and Ordovician. 2 like period in time very important for like Earth history. And if we look at the vanadium concentration, there was like some striking differences from like a certain like, let's call that background level, but still like in 200 ppm for like the Cambrian, to a skyrocket like 4,000 ppm in the Ordovician. And we wanted to know why. So we say, hey, let's try to like use like bring this sample to like the synchrotron. And here, before like showing you the data, I want to talk about the importance of like using the right standard. And by that, I mean like, yes, most of you can use some database. Most of us, we can use some database. But I want to emphasize something. Nothing beat to also like make your own standard, to interpret your own data. Because like studying whole chain rocks, it's a complicated matrix. And to improve your interpretation, you need to like develop your own set of standard. So for a long time, all the people who are like studying vanadium speciation, whatever the purpose, were mostly considering these 3 standard. And with Liebo, what we did is like we decided at least to add like two other, you know, like you see, this sulfur compound, vanadium 4 and vanadium 3, but surrounded by like sulfur. And we went to like our like a place I often go, and a special place in my heart, like JSCAR sector 13 at APS, and we collected like this great data. So this is just exams, okay? And here, like this talk is, I don't want to spend too much time on the technicality, or like even, you know, like I'm a user, as Jerry said, you know, I'm not a beamline scientist. Let's look about what it means. When we apply the linear combinatorial fitting, you know, like, and basically process the data, what we found was like, there was a change in the redox state. Let's talk about the redox state of vanadium. In the Cambrian, it was mostly around like 4, but as you like progress toward like the Ordovician, where you have like very high concentration, it became like, you know, like from 4 to 3.8. And what we identify in that matrix was like 2 different phases. Basically, like it was mostly vanadium 4 surrounded by sulfur. And here I want to put, I'm not saying we have vanadium 4 S2, you know, like we interpret it to be like vanadium 4, probably surrounding by sulfur, and our assumption was at that time with like sulfurized organic matter. But the proportion of vanadium 3 as oxide became quite significant during the Ordovician. And what was even like more interesting is like we could find this great relationship between the concentration and just like the concentration of vanadium 4 surrounded by sulfur. So like this was the point of this paper, to kind of propose a new like species in black shale that was never reported. And at the end of like that paper, we did propose like a new model, because in the past it used to be a straight line. Vanadium 5 is going to become vanadium 4 and vanadium 3 oxide. But now like I think like vanadium 4 is surrounded by sulfur, is the significant species in black shale. And of course, sometimes we will have some vanadium 3, but we cannot explain really why. And with Liebo, we came with like some like assumption, and I think we're onto something. And we are continuing that work actually still with like now like a PhD student of mine, Bodhidharma Mankurov, still like about like the alum shell, but we study that well, you know, like with Liebo, and now we are more like studying like these 3 wells in Estonia. This is a collaboration with like the Geological Survey of Estonia. And basically we did the same thing. This time there is no like, there is still a high enrichment. I want to show you 1000, but we are not at the 4000 level, but it's still high. And this sample were run at, I think if I recall, at Soleil, on the Puma beamline. And what we found also, by the way, what I want to point out, we also collecting more like standard, because again, we did synthesize our own and also added for like that trend, thanks to like our collaboration with the group in Saskatchewan, and I forgot Matt, you know, and they published some great study about vanadium speciation within oil, and there is like this porphyrin complex that actually we were also able to identify in black shale. But here, let me show you like the main finding. Here also, so we have this huge basin, alum shale. On the western part, we identify it was molybdenum 4. On the eastern part, it's the same. But here, like, let me show you like a new figure. With like at Puma, we were able to also, we did like molybdenum and vanadium at the same time. And I will tease you with like this last slide that Bodhidharma presented at Goldschmidt not too long ago that attracted a lot of attention. in one core, I mean in all the core, but like the vanadium oxidation state display like an inverse relationship with the molybdenum oxidation state. And this is very interesting. And here I will mark my first break for like any questions.
All right, I'll remind everyone to please put questions into chat, and I'll start off with one. You've emphasized with good reason the importance of having an appropriate reference set. Did you consider maybe using X-ray emission spectroscopy as a complementary way to get at information about oxidation state or ligand identity?
The answer is yes. So like I've been as a curious user, I would say like I'm always eager to like dig into like more like to broaden my like scope of synchrotron techniques. So I'm not going to say, but yes, and I'm still looking for like what I call like expert, or like some people who would like help me like to like start using these new techniques, because it's on my radar.
Okay, there's likely people in the audience who will reach out to you after the talk. That's great. Not seeing any other questions right now, I'd say you should continue, please.
Thank you. So now we're going to move to like the Paleo-Redox application. Here, keep in mind, it's still about trace element in black shale. Actually, even vanadium is a Paleo-Redox proxy. But here I wanted, the whole reason why we want to know the speciation is to promote like sustainable mining. We don't want to like, we need these resources. And so we cannot just go and dig somewhere where we know we have a lot, where we could go at a different place where it's going to be much gentle for the environment and less demanding for like the energy and other things. Now about the past. Chromium isotope now. So chromium isotope is like a Paleo-Redox proxy, particularly useful for like studying like the early Earth oxygenation. And I'm not gonna like make a lecture about chromium isotope right now, but like the whole reasoning behind it's because there is a large fractionation when chromium-6 is reduced to chromium-3. And that would like means like that would require like manganese oxide. So some paper have shown that, you remember I showed you this figure before, you can have like several what we call like paleo proxies, indicating like you can track like the change in like the oxygen. And right now, so like this is one just showing like I want you to concentrate on the red dot. This is going to be in black shale. And you see like there's no fractionation before what we call the great oxidation, because there was no oxygen. And you can start to see like some increase as we progress toward this second stage with Proterozoic. And then when we reach to like the Phanerozoic, the explosion of life. So the chromium isotope have led to like wonderful finding. But because there is always a but, when we want to use chromium as a Paleo-Redox proxy, only like the autogenic fraction matters. By that, you remember I told you like you want chromium-6 to be reduced. So chromium-6 on the Earth cross, chromium is going to be mostly 3. So you want like you want to follow the process of chromium-3 being oxidized to chromium-6 by like some evidence, in that case of manganese oxide, most likely. And then this chromium-6 is going to be reduced as it's being buried into like the oxygenic setting. And this is like the theory behind. And of course, so you have like this part of the chromium is going to follow this path, but you have also like the detrital, just like the particle of chromium are also going to be brought from the continental mass into like the ocean. To use and especially for like the model, when it's about assessing and calculating what was like the PL, basically it's like what was the level of oxygen back in the time, you need what we call the isotopic signature of chromium within the oxygen fraction. How do we find that? It's super basic. This is why like sometimes I wish like the Paleo. One way is to like just use like the chromium titanium ratio. Why is that? Because titanium is like an indicator of detrital input. This is what I call the basic one. Another possibility is to like make some sequential extraction where we're gonna have like some gentle attack, let's say with some like weak acid that's should only target like the autogenic phases. And you can see on this paper now, like a few years ago from Chappaz, between the bulk and what is autogenic, you have like at least significant difference. So, and that's going to matter if you want to reconstruct what was the oxygen level back in the time. And here, like I want to emphasize, the whole community using the isotopes spend all their effort into the analysis, and the analysis are like done in the best way it can be done. Yet they neglect one aspect, and this aspect is no one has checked that you can use this approach either like to divide by the titanium or like even the sequential. So again, we took like a selection of sample to like one of the beam. And here what we found. So here we measure like the speciation. So here I'm just presenting the data for like two modern systems, but they are like reduced Peru-margin and Chappaz and demineralized, which is like what we call the oceanic, anoxic oceanic event 2. And we measure chromium speciation at different location. We had like different standard, you know, we apply linear convergent fitting and everything. And here, like what we found because with that approach, we can also, from direct measurement, determine the chromium autogenic fraction. In black, you have what we found using synchrotron technique. And here, for example, that is with leaching. As you can see, sometimes it can be up to like 100% of difference. This is major. This is major, and the community using isotope cannot pretend it does not exist. Because here now I'm showing how it can influence. This is a chromium isotopic signature. Sorry, on the y-axis, it doesn't show. In black is what would be like, because they modify the bulk measurement to give like the autogenic chromium isotopic signature. And for like all the basin, you see like for Chappaz basin, we can have sometimes up to 60% of difference. And that's going to totally change like the model and how we use isotope. Again, it's not about how like they run the isotope, it's how like they use the data. And it's the same also for like the OA2 event. Now, switching to like a different element, my favorite one, if I were to ask you, molybdenum. So molybdenum is extremely important for two reasons. First, it is needed to fix nitrogen in any eukaryote system because of like this tiny molybdenum here. If you do not have that atom within that enzyme, you cannot fix nitrogen. And also, to study like the early Earth oxygenation, it's great because it shows like a very constructing behavior when in water. This is in water on this. If you have oxygen, you're going to have high molybdenum concentration. But if it's like sulfidic, so see, no oxygen, sulfide, you're going to have like a minimum concentration. Okay, and that has led to like an observation of different enrichment. Now, this is in the black shale, and people have tried to associate different level of enrichment to like, you see like this anoxic, oxenic, and condition, which I think we should move away. I told you that. So molybdenum is great to study like the Earth history. And a year and a half ago, we published like this review paper with a former PhD student of mine. And what we wanted basically to show is it's complicated. I'm not going to go through it, But again, 10 years ago, people were only considering like almost a straight line, like for like the vanadium. What I want to like emphasize, because you're going to need to know that, is for like a few slides later on, when you have molybdenum in oxic water in presence of sulfide, a lot of people were assuming it would end up in MOS4. Okay, so it's not a reduction, it's a substitution. We call that a thiolation. So let me now show you, like, I'm spending like now close to like 12 years working on molybdenum using synchronous techniques, and I'd like to give you like a quick walk through like our findings that change the way we see molybdenum. It started almost with like this foundational study now from a lake, sulfidic lake in Switzerland, and here we had like this long core of 10 meters, and for the first time, I remember it was not at Chicago, it was at NSLS. We brought this, we had 10 samples that we were able to preserve anaerobically. And we measure like the molybdenum speciation. And as you can see, like, this is exempt. So first you can see like sometime pre-age, sometime no pre-age. But here I want to point out directly to like the Fourier transform. In some of the sample, we had only like one signal, which we attributed to sulfur, and other, we had like a combination of oxygen and sulfur. So at this time, we could not decide if the oxygen was because of exposure to like, actually like oxygen, because even during measurement, we run that under nitrogen atmosphere. But one thing that it was the first study, we showed that molybdenum 6 could be reduced to 4, but not as molybdenite, not as MOS2. And we continue with that path. It was with Teisdal from Copenhagen, and we wanted to like see if molybdenum could be associated with particulate organic matter. And this is because of the famous relationship that can be seen in black shale between molybdenum concentration and TOC concentration. So we use bacteria, but just to kill them, basically to provide like particulate organic matter. And then we use different like molybdenum and sulfide concentration. Importantly, there was no iron. And what we found is that molybdenum 4 can be associated with particulate organic matter without the presence of iron. It was thought like iron was required, and actually this study showed it was not. Still moving on with like, by the way, all these studies, they were experimental. They are now like part of my huge database of standard, because I want to emphasize for like the one interesting in applying like synchronous technique for like Paleo-Redox, you need to build up your database of standard. And it means that, yes, you're going to have to do some experiment. Now, we also looked with like a former product of mine, Megan Wagner, at molybdenum dissolved. So the previous slide was about solid particulate organic matter. Now it's with dissolved organic matter. And as you may know, dissolved organic matter is this huge molecule, a nightmare for the pure chemist, but they have a huge capacity to like bind metals. And because it was the first try, we were humble, and we decided actually to just start with like organic acid. So organic acid to like just mimic some functional group within like the organic matter. And we tried this experiment with oxygen basically, and under sulfidic condition. And long story short is we were able to show like we form like these intermediate spaces, sometimes where iron is present. And with that, we were able also to demonstrate that when molybdenum is going to be bound to organic ligand, I thought my assumption when I wrote that grant, it was the binding would occur via like the sulfur atom. And actually I was totally wrong. This is the beauty of like hypothesis. And actually the binding occur like via like the oxygen atom. But most importantly, it disemphasizes the role of MOS4. Remember in my like complicated story, I show you about, hey, everyone was assuming the alpha and omega of the molybdenum was MO4 and MOS4. It is not. So there is like somehow like some people who like judges for molybdenum always want to like have what I call a unified model. By that, it's like there's going to be only one explanation for like one element. In my opinion, it's always more complicated. And the organic matter pathway I just talked about is also like happening at the same time as what I'm going to say, like the iron sulfur pathway. And that I want to clearly say it is not with pyrite, you know, because for like 15 years ago, people are like, oh, the story is molybdenum at soaring pyrite. No, it is not. I publish about that. Contact me if you need like the paper. But with my colleague now from Trent, Vorlicek from like University of Minnesota Mankato, and following the great idea by Georges that with amnitio calculation came with like this idea that molybdenum could be bound with like iron in sulfur as cubane structure. And we wanted to put that to the test. And all the credit go to Trent, who like spent almost a year designing this experiment. It was very challenging, but we made it and we ran these samples to APS. And what we found was really fantastic because we found that it was molybdenum 4 as predicted by the model, but it was not molybdenite. Actually, when we do like, we had beautiful data quality. When we did like the EXAF modeling, we prove it was cubane. And that is major because also like that structure is similar to like the one that was found in Lake Cadagno. And also very similar to the one in the enzyme, the FEMCO. So maybe back in the time, this could have been like, I call that a Lego block available for like the early form of life to incorporate in their structure. Now, moving on with some collaborators from Canada, when you look at the past, you always want to make sure like you're going to interpret an original signal and not like what we call a diagenetic effect. So like a secondary signal that would have altered like the original signal. And we decided to study like this black shale from Quebec because we had this interesting profile where like you have what we call the structural level, but we had this micro enrichment, and I mean super high enrichment, but very like thin, you know. And the question by my colleague was like, are they real? You know, like could we imagine there was like for a short period amount of time some like reducing condition, or are they due to like diagenetic effect? So again, we took that to like the beamline, and what we found actually like was like very surprising because here we found like the presence of two phases, molybdenum bound to sulfurized organic matter, but here molybdenite. So when you have molybdenite in black shale, it should be like trigger an alarm. It's mean what? Watch out. Maybe like this is not the best sample to use for paleo reconstruction. And last slide before like the break too. So like I mentioned OA2 for like the chromium isotope. We can also go younger in time. It was 80 million years ago. In the middle of North America, we had an interior sea, and with like some collaborator, we apply what we call like traditional geochemistry, you know, not even isotope. It was just to look at the concentration of molybdenum between two cores, okay, two cores. And when we just look at what I call the traditional approach in geochemistry, it just said like it was axenic. Why is that? Because you have certain enrichment of molybdenum at both core, and you have like this is associated with what we call the iron speciation technique, but here it's not about measuring iron speciation. It's a sequential correction that is widely used by like the Paleo-Redox community. But here, if you like consider these two, you would like assume like they are like the same redox condition. We wanted to try that. And we took this sample again to like a beamline. And what we found is like actually just by looking at the oxidation state between the one that used to be at the bottom of the basin and the one on the shell, you can see the one on the shell is more like slightly oxidized. And just by looking at the Fourier transform, not even like any modeling, just looking at your eyes, you can see like for like the sample at the bottom, you can see a signal of oxygen and sulfur, whereas for like the one on the shell, it's mostly oxygen. So with that, we were able to refine that at the bottom, it was certainly like slightly sulfidic, not too much because you can still have oxygen, but for like the chemocline must have been right at the level of like the core on the shell. And I will mark now like my second break.
Thank you. I'll remind everyone to put questions in the chat. We'll start with a question from Matt Newell.
Hey, Anthony. Thanks. It's great to see you, and this is really fascinating stuff. I would have a question about later stuff, but you showed about at the time of the first break, the vanadium data at reduced conditions got complex for whether there was oxygen and sulfur co-reacting. And my question is, what is known about the sulfur concentration or the sulfur availability at the great oxidation event? Was there also like an injection of sulfur, a sulfate at that time? Like, was it volcanic?
Thank you, Matt, for asking this question, because I don't have like, but you are right. I can see like you're right onto the right question. And actually it's funny because we put a proposal to measure sulfur speciation in the same sample.
Yeah,
and why is that? Because as you suspect, yes, we have sulfide, we have like the sulfur isotope, we even have some nanoseams, so we have cool mapping. It's complicated because the sulfur is not only inorganic and organic. But where it's become interesting, my theory now, to explain like the formation of vanadium-3 is you need to have sulfur 0. It's something like people, I'm going to refer that as polysulfide. Right. For like the paleo community, it's something like it's totally ignored. The people working on modern system, they are aware of that. You have like the sulfide, but you have also the polysulfide. And right now, our theory is like you would have like to form vanadium-4, you need the presence of sulfide, -2. But to form 3, because you need like, like 2 redox couple, you need like the S0 somewhere. And we want to put that assumption to the test by like looking at sulfur speciation in the exact same sample and phases we measure the vanadium speciation.
Sure.
Because yes, we think like the two systems are like almost tangled. Yes.
Okay, great. Thanks.
Okay, second question, I'll paraphrase from the chat. Could you expand on the surprising inverse correlation between the vanadium and molybdenum oxidation state for the alum shale data in Estonia?
So this is something we are currently working, just so you know, like it's a first year PhD student, he's bright, he's body jar, and we just collected this data a couple of weeks before Goldschmidt. So it's surprising, it's amazing, because, one thing I love to do is also like teach the young generation about how to use synchrotron. By that, I mean also like processing the data. It takes time. And bear with us. We hope like within the next few months to have a manuscript we're going to submit, but I didn't show you all the data we got now because it's part of his PhD project.
All right, thank you. You should continue.
And now the last part of like the presentation. So let's go now using microfocus beam. And for example, for sulfur, people have been using that at EOS0, even with SunWeb or so many other places. And I wanted to look at now like the molybdenum speciation, but within like different spaces, but at micrometer resolution. And for that, I run some sample from France. So as you can see, like hope you can see, it's like right at the border between France and Switzerland. It's called like Orbagnou. And it's in like the Jura mountain, of course, because it was like from the Jurassic. This is what gave the name. And why we decided to like use it, because here you have such high enrichment of molybdenum, and also like a high level of TOC. But even better, when you scratch the rock, just that you can smell sulfide, you know, even very old rocks. So like, and some organic geochemists characterize the organic matter and it's sulfurized. So go to like the paper by Nicolas about that. He is a specialist of this formation. So here I just want to tease you, because we're almost done. We have like, again, this is recent data. Here xanths, as you can see, for those not specialists with like molybdenum, speciation, one side we don't have any pre-edge, another side we have some pre-edge. The one where we have like the pre-edge is going to be like we targeted the organic matter right into like that phase here. But for like the other one, we went more into not the pyrite, okay, but more like what we would call the matrix. And here we found it's exactly similar to the cubane and the Cadagno speciation. So it's at one formation, we can see some huge heterogeneity at micrometer resolution. We did the same thing, the back-end formation in Canada. Here also, those are data taken at sector 13. And here also what we found is like super interesting, because here we even targeted the pyrite in addition. And for like same sample, you can look at organic matter, pyrite, and of what we call the matrix, and you have a different molybdenum speciation. And this is going to be like extremely important for interpreting the isotope. Speaking of the isotope, hey, perfect. The importance of transition, the student. I want to like make sure everyone, because the crowd may be more familiar with synchrotron, isotope, like I introduced the chromium isotope, molybdenum isotope are like very powerful. And the reason behind is the current modern ocean here has a positive isotopic signature, modern seawater here. It's because of 98% of the bottom of the ocean is oxic, and you have manganese oxide. And when like molybdenum is adsorbed on manganese oxide, you're going to have like the light element going on the manganese, leaving the heavier in the water. This is why it's it has this signature. Now I want to point your attention to like when it's oxenic, you know, basically sulfuric. When it's strongly oxenic, there's no fractionation. So basically, like with that assumption, people have been using molybdenum isotope, assuming it was very strongly sulfuric in some ancient system, because it would match what was to be like the ancient seawater isotopic signature. In theory, that works, you know, and some good paper works. What is tricky is like, it's very hard to have like strong sulfuric condition. And most of the time, we're going to have what I call in between. In between is like, yes, you are going to have sulfide, but it's not going to be like extremely high sulfide. It's going to like promote MOS4 and other like reaction. And because you have like all this intermediate, I know you don't probably remember, but from MO4 to MOS4, you can have like all different intermediate where one oxygen atom is going to be replaced one at a time by a sulfur atom. And that can induce also some fractionation. So some people have been trying to like figure out how to better explain constraints the molybdenum isotope, but it's still changing. So let's put that to the test with like some studies that use isotope and speciation. Let's start with like something 30 million years ago. My colleagues now, like the group from RUL, led by like Alex Dixon, they published like this great study not too long ago, and I'm putting in prep, so it's a paper I think in APSL, this figure. The point is like, you see like you can, this is what we used to be Europe 34 million years ago. And I want to point out your attention to like this part of this channel used to be oxic. If we look at the molybdenum isotope, then it became anoxic, and then it was more lagoon that went back to like something weird. So let's start actually with the iron speciation, which is not, again, not measured, but like, if you just look at that, in between these two, it's going to tell you it was oxenic. So just ton of sulfide, okay? So this is a tool I want to point out that is like used by like countless group. Now, they did measure in the study like uranium and molybdenum isotope, which bring a lot of nuance. And by that, but still, they show like it was probably like sulfidic, but not as highly sulfidic as suggested by like the iron speciation. So they're really like low order, you know. And I run like a selection of sample from this peak, because what was puzzling me was you see like this kind of same gray area, you have like this extreme. So I did run like the molybdenum speciation, and here what we can find. And I want to attract your attention. I run, I think, 8-9 samples for Xanth and Exaf, and I'm going to show you like something interesting. And you see, you have like on purpose the yellow, that's going to be like we'll see corresponding to like sometime minimum, but not always maximum, and the blue population. And here, like where it's become like something where like measuring speciation for any like paleo proxy can really enhance the interpretation. They could not figure out any differences. With now, when we plot the oxidation state versus the isotope, we can see what I call two populations. These two populations indicates two different regime in the redox condition. Something like not even the concentration and or like the isotope could see. And these two populations can be tied, and even like, if we just look at the Fourier transform, not even like modeling. This population here, it's going to be mostly through oxygen around molybdenum, a tiny bit of sulfur. And the yellow are going to be like the one with mostly like sulfur around. So now, by combining both, we can address, you know, like the transition in the past, because like systems are constantly fluctuating. They are not stuck, you know, like, and here we need to apply this tool to like so many like ancient systems. And now like the finale. So at Goldschmidt, I couldn't resist to talk about that because there was this sort of third between like two prestigious groups. And it's about some of the oldest record of available to study like the Archean. So this paper led by Aryan Ambar in 2010 now, I think in Science, you see, this is a great oxidation event from a core from Australia, 2.5 billion years ago. If you look at the molybdenum, you have a peak. But here, because it's the beginning of like the oxygenation, it was not interpreted as like, you had a big enough weathering from the continent that brought more molybdenum into the ocean. What was tricky is like the iron speciation, keep in mind the expression, tell us it was sulfidic, crazy sulfidic, oxenic. So profile 1, Nature paper, profile 2, Science paper. Now like they did measure a few years after like the isotope. The isotope just ended up in a very good journal, GCA, but somehow it didn't make like the flashy journal. And the reason is because it was very tricky to explain this variation. They came with 4 different scenarios. So I decided to put that to the test. So I run, they are difficult to acquire, so I could only say I got 6 samples. So the first thing is like, I wanted to like compare those with like some altered black shell. Because these samples are so old, we need to make sure that it's not altered, there's no diagenetic processes. So I picked Zanelloga formation from some colleague in Europe, and we know this one has been altered. And I measure speciation in both. And I selected the 6 because they're like so rare, based on the molybdenum isotope distribution. I wanted maximum high isotopic signature, low isotopic signature, and intermediate, and all around like what we call the famous whiff of oxygen. So let's start by like the Zanelloga. In the Zanelloga, all the molybdenum is molybdenite. It confirmed, you know, like our first paper with like Hamid from Canada, molybdenite is a good indicator of metamorphic or like diagenetic processes. Now here what we found for like microshell. I remind you, high isotopic signature, intermediate, low. We did find jordicite is amorphous, you know, like the Cuban phase that we synthesize with trend. And MO3 is going to be an analog for organic matter. What we found is a perfect, an excellent relationship between the oxidation of molybdenum and the isotopic composition. And with that in mind, we can revisit what previous studies have claimed about the redox condition 2.5 billion years ago. And we can like bring nuance. So like, it's mean before yellow, it was probably like tiny bit of sulfide, what we call weak ammonia. Then at the maximum, it was not oxygenated, of course, but it was probably ferruginous. And yes, only after it became like sulfidic, but not as sulfidic as suggested by like the iron speciation technique, the extraction. So this is the end of my presentation. Thank you for your attention. And if I have one take-home message, do not neglect the heterogeneity of the critical metals or your Paleo-Redox proxy. Thank you.
It was wonderful. Thank you for the great talk. Matthew Marcus, were you able to stay? Do you have a question?
There we are. Yeah, I was wondering about the organic matter and how that might be related. After all, I assume that's why black shale is black.
Yes, absolutely. So like, yes, you're absolutely right. The reason why it's black, it's because like the black shale, when they were formed, they trapped a lot of organic matter that was not exposed to like the oxygen. So it was preserved into like the rocks. And the paleo community have had a hard time trying to investigate the mechanistic relationship between their tool and these phases. And there are many explanations to that. It's because it's always more difficult. Even experimentally, it's not as easy as working with mineral phases. Mineral phases, you can synthesize them, you can even buy them. So for different reasons, there was an emphasis more about trying to directly measure the real stuff, which is good. And somehow it put less emphasis about the role of organic matter. But I agree with you, organic matter is like extremely important to a point now, like having some proposal using some more like UV beamline, one in Europe. I'm gonna go like actually like in a few weeks to like study organic matter.
I run a Stixum that can do carbon edge.
Yes, so like carbonate also, you mean like at what angle would you like to like, because the carbonate has been studied in terms of course, isotope, but would you have in mind more like in terms of speciation or like distribution?
Yeah, distribution of functional groups.
Oh,
So
that, no, like
as a nanoprobe.
Oh, that would be
the
fantastic.
disadvantage is that you have to use it, you have to do a thin section.
Which we have plenty of. This, yeah.
So you have to fib it or microtome it.
Very good. It sounds like you two should talk.
Yes, yes.
I'll stop it there because we have a couple more questions.
Also,
thank you, Matthew. Oh, and also Matthew has to go. Yes, Yang Ha, you had a question.
Yeah, hi. Yeah, I'm not very familiar with geochemistry. I saw you use a lot of XFs to do the assignment. Based on my understanding, XFs only give you the local distance. How do you correlate that with your species assignment? And how's that related to the edge energy, which tell you the oxidation state of the materials?
So the way, like any like exact study in material sciences, chemistry, you know, like even like mineralogy, we have access to like huge database, you know, like, and we start from what is known. This is why like we even start with our own standard. where like that we measure everything. And also I'm not the only one working on, let's say, molybdenum, many elements. But we start by like, first we concentrate mostly on xanths, because just the xanths can tell us a lot.
Yeah.
The EXAF, we're only going to apply it when we have like good data quality, which is unfortunately not always the case, because it depends of like, interferences and what's going to come. The rocks have like basically the whole periodic table, and we only apply that to a certain degree, because we are not interested in going too far away, the molecular environment from like the element of interest. Because to answer a question related to like what we're interested in learning, first and second shell, maybe maximum third shell are important. So we use known structure, and we start by like modeling the first shell. They say it. I mean, I'm not going to do like the thing, but we use like software like Artemis or Larch or any other one, and we go shell by shell on mimicking and slightly adapting with known structure all the standard that we got. And then at some point we stop, because we are very happy if we go like for molybdenum, for example, what is very important is this ratio, what I call the oxygen-sulfur ratio. As long as we can quantify the coordination number, like with like, of course, the error and on our appreciation, it's an enormous amount of information, because with that, we can better speculate about what was like the amount of sulfide in the ancient ocean.
Okay, thank you. And one minor comment. So there is another cofactor called the VMO, which is the vanadium substitute of the VMO. Sorry, there is a vanadium substitution of the VMO, which replaces.
You're absolutely right. Yes.
Vanadium, yes. And since you have all those tools, you might want to also consider just apply some of these on similar systems. Yeah.
The thing sometimes is I see what you are referring. I wish I could have quoted like this. A few years ago, there was a great paper in geobiology about how like vanadium was so important in the ancient ocean, and yes, related to like fixing like nitrogen. The thing is, sometimes it's difficult to acquire or sensitize this enzyme, but like I would love, even if you have like your N on that, next time I will run it, because I always want to like build and increase like the database of standard, or let's call that non-structure.
Thanks.
You're welcome.
Okay, the last question, Sechi Lee, could you ask your question?
Oh yeah, could you hear me?
Yes.
Okay, great. Okay, so before I advance my question for the vanadium in the biological, actually we observed an isotope signature recently in the seawater, which I think may indicate the biological involved vanadium in like maybe nitrogen cycle. We could discuss that later if you are interested in I'll send you the link when I do that. Anyway, I just want to let you guys know that there is something interesting about the isotope signatures. My question is about the molybdenum actually. So it looks like there is a correlation between the molybdenum isotope and the valence state of molybdenate in your slide. But so there is a research announced the California margin by Paulson et al. 2006. The bottom water of a salted basin in the California margin also present the ferruginous condition. So if we make a comparison between the ferruginous bottom water in Soledad and the exenic water column in like Echo, actually they present very similar molybdenum isotope signature, like a plus 1.5 to plus 1.6. I think are very, very similar. I mean, if there is a oxidation state change of molybdenum from the ferruginous condition to the exenic condition, I guess the two sites in the modern ocean should also present similar, like the isotopic signatures, but actually this is not observed.
So, Sikshi, for to make sure I understand your question, you are like saying, like, I'm gonna rephrase it, and like the same molybdenum isotopic signature can be observed for like ferruginous system and also like more like euxenic system. I agree with that. You're right, but it turned out I have some unpublished data about the molybdenum speciation in Caraïco Basin. And I do not have actually like access yet to like some ferruginous system, but I would bet like this, I would speculate. You know, it's no, we're not in. I would speculate the molybdenum speciation is going to be quite different, because I can tell you for like the Caraïco Basin, it's mostly molybdenum. It's closer to like the Cuban. We have a mix of Cuban structure and a little bit of organic matter. Whereas for like ferruginous, we won't see. My assumption is we won't see any of the Cuban structure.
Okay, because based on your last slides, looks like the ferruginous and the euxenic, between the two conditions, the molybdenum fractionation can reach around 0.4 per mil actually, which is significant. So I guess if this is true, I guess there should be some observations, or like we should be able to observe it in the modern marine environments. We have some sediments along the California margin, the basic ferruginous condition is that if you're interested.
But I know we talked before, but like I would love to like explore like this question with you, you know, like by combining like isotope, because I think my whole point is this talk is like, by the way, if it's not clear, so it's not a magic technique. You know, you cannot just use isotope, like you cannot just also just use like synchrotron. You know, by combining different techniques with different approach, maybe like you can start to become close to like the reality. And I would love working with you on that. Yeah.
So we've run a little bit over, but those were excellent questions and discussion. And I will thank everyone again for coming and remind everyone that the talk was recorded and will be posted on the Global XAS YouTube channel. All right, with that, I'll stop the recording. We should all thank Anthony.